the Theodore Von Karman Prize lecture, and it will be given by Richard James, I know him as Dick, from the University of Minnesota. The Theodore Von Karman Prize was established in 1968 and is awarded for a notable application of mathematics to mechanics and or the engineering sciences made during the 5 years to 10 years preceding the award. Dick James is the Distinguished McKnight University Professor in the Department of Aerospace Engineering and Mechanics at the University of Minnesota. He, with Sir John Ball, he's Chief Editor of Archive for Rational Mechanics and Analysis. He's a Fellow of the American Academy of Mechanics. He was awarded the Warner T. Carter Medal by the American Society of Mechanical Engineers, the William Prager Medal by the Society of Engineering Science, and the Brown Engineering Alumni Medal by Brown University. His main area of research is phase transformations in materials, especially shape, memory, and multiferroic materials, and large and small scales. And the title of his lecture is Materials from Mathematics.
So thank you for your kind introduction, Irene. And it's a great honor to be able to give this lecture. And I was particularly humbled when I saw the previous list of recipients, beginning with G.I. Taylor. So what I'd like to speak about is some recent work in which some new materials have been discovered by use of mathematics. But somehow mathematics has also played the key role. So most of the materials I'll show you were made in my lab, which is a very basic lab. Nobody in material science would consider my methods of synthesis cutting edge. It would be the most basic classical methods. So it's not about the synthesis here. It's about somehow the ideas that were used to suggest how you should change the compositions of materials to achieve some interesting materials. So I should say that that's not completely true, because some of the materials I'll show you were made by methods of actually 500 of them, on the order of 500 of them were made by methods of combinatorial synthesis by another group. You'll recognize that when it comes, and that's a very sophisticated and very interesting method, particularly for mathematics, because it's possible to make many, many materials. As Irene said, my area, the materials that have always interested me are materials that undergo phase transformations, and these are diffusionless phase transformations, so there's no diffusion. There's just a change of crystal structure, maybe a cubic crystal to a monoclinic crystal. So there's a distortion, therefore elasticity plays a role. And there's lots of interesting effects because of the fact that crystals themselves have interesting properties, like the hardest materials are crystals, magnets are crystals, ferroelectrics are crystals, superconductors are crystals. Then if you have a phase transformation between one crystal and another, one thing you can do is turn on and off properties, and I'll describe an example of that later. No phase transformation would be very interesting unless you could do the phase transformation many times. So the reversibility of phase transformations is a critical problem, and that's the subject of my talk: is how to make phase transformations reversible. So I'll start with an example of a phase transformation which is not reversible. This is just cooling a specimen of the pure element tin. So tin undergoes a phase transformation at about minus 15 C, and this is what happens to a tin crystal when you cool it down. So you can see that I love this movie because the little parts break apart and then they break apart again. And of course, you can only do this phase transformation once. So this is an example of a highly non-reversible phase transformation. It happens in the pure element tin. There are many, many of these kind of diffusionless or so-called martensitic phase transformations in the elements even. In particular, if you change both the pressure and the temperature, you can induce many phase transformations. So People would say that this is the reason that this is not reversible is it has such a big volume change that it tears itself apart. I don't believe that explanation, as you'll see later, but it's the accepted explanation. So here's so I'm going to measure. I could measure reversibility by how many times can I go back and forth through the phase transformation, or I can measure a certain property like the latent heat. Each time I go through the phase transformation, does it give off the same amount of heat and reabsorb the same amount of heat? And so any property can be used as a measure of the reversibility of phase transformation, but I'm going to use a very, very important measure, and that's hysteresis. So this is a phase transformation between a cubic phase and a tetragonal phase, one of the most simple kind of phase transformations, where this cube at a certain temperature, theta C, distorts by elongating along one direction. And there's 3 possible symmetry-related directions, so you get 3 so-called variants of the low-temperature phase. The terminology, this is martensite, and this is austenite, and these are the 3 variants of martensite. And if you pass back and forth between this variant and this variant, which you can by applying stress, you see that this is some measure of the stress, and this is the measure of the volume fraction of this guy versus this guy. You can see that it transforms at a different stress on going one way as it does in the other way. And that's a so-called, that difference defines the hysteresis, and it's a measure of the reversibility. And in fact, the area in this loop is the measure of the energy of your loading device, which is dissipated by the material. You can also, it's in fact, most of my talk is about thermal hysteresis, and going back and forth between this phase and any one of the 3 variants, or any microstructure of the 3 variants. You also have a hysteresis loop. People usually fit it by a parallelogram, and they define it therefore by these 4 temperatures: MS, MF, AS, and AF. So a key thing about hysteresis in these phase transformations, in diffusionless phase transformations, is quite surprising, actually, is in that stress-induced case. So if you go back here and look at this case, then this is that hysteresis loop, and it was done with loading this crystal in a biaxial way. I won't describe how it was done. And the percent of one variant versus another was measured by taking a window on this picture and computing the area fraction of the colors. And that's what each dot corresponds to one of those measurements. In fact, the measurement, it turned out it didn't matter where you took that measurement on the specimen, which is a very important observation, but I won't go into that. But anyway, the point is that the hysteresis loop these are the rates of loading. That's the actual period of the loading. It was periodic loading program, and this was 10 seconds, and this was 1,000 seconds. And you can see that the size of the hysteresis loop is very nearly independent of the rate of loading. That's so-called rate-independent hysteresis, and it's the typical hysteresis in these materials, also for thermal hysteresis. Okay, so you can look in textbooks, and you can find out what causes hysteresis, and I'll tell you, summarize the main ways, the main ideas. Perhaps the most accepted idea is the pinning of interfaces by defects. So when you have a phase transformation, an interface moves through the material. There are inevitably some areas of the material which are non-transforming, usually precipitates, and this gets stuck on these precipitates, and you have to lower the energy well of the new phase in order to have a free energy decreasing path and cause this interface to break through the precipitates. And this is the origins of hysteresis. Happens both ways through the phase transformation. That's probably the most accepted idea. A second idea is a very interesting idea and hasn't been completely worked out mathematically as far as I know, is an idea of thermal activation. So if you could take one of these materials and you could plot the potential energy surface as a function of all degrees of freedom of the system, so it's of course ridiculous, but there would be, I'm parameterizing it by the positions of all the atoms in the system. But imagine you could do that. People, believe that you would have a very wiggly surface, and you would have some deep wells corresponding to the variants of martensite. Those would be the low temperature stable phases of the material. Now, the state of the system would be given by imagine it could be given by a dot on this surface, and the dot would be moving around this surface. In fact, the equations of motion of the dot are the equations of molecular dynamics. So the belief is that as you raise the temperature, the kinetic energy of the system increases, and it's at some point it jumps out of this well and it's delocalized on this surface. So as indicated here. And that corresponds to the phase transformation to the austenite phase. In fact, it may not even be at a local minimum of the potential energy. It may even be at a local maximum, many people believe, of the potential energy. Then as you lower the temperature again, it falls back into this well. But as you can imagine from this picture, the temperature at which it falls back into this well, because it has to find that well in this very wiggly surface, should be quite different from the temperature at which it finds its way out of the well. And that's the thermal activation origin of hysteresis. By the way, that does need to be worked out in this context. There's not a good analysis of this in this context. Finally, I'll mention another approach, which is the following, is you imagine the unit cell of the austenite phase, and now you imagine a one-parameter family, a path between the austenite and, say, one of the variants of martensite. So this is a very popular thing to do, and you compute using first principles calculations the potential energy along this path, and the parameter of this path is called a reaction coordinate. And you do this for many, many paths between these two, and in fact, there are mathematical methods, for example, the nudged elastic band method, which helps you find the lowest energy barrier between those two phases. Right? So you find this lowest energy barrier, and that's what the height of that should correlate with the hysteresis. That's a belief. Okay, so the explanations I'm going to give you say that this is completely irrelevant, this barrier, and that if there's any barrier in this picture which is important, it's not even a barrier, it's this part of the curve and this part of the curve. Okay, so those are the accepted ideas about hysteresis. And so now I want to tell you a fourth idea about hysteresis, which I think is the key idea, and it's the one that's used to find these materials. Okay, I need to define some things. The linear transformation, which takes this crystal structure into this crystal structure, I'll call U or U1. In this case, it's given by this matrix in the cubic basis. It has eigenvalues, and the middle eigenvalue of this matrix is going to play an important role in my talk. In reality, this is a small remark, but it's an important remark. In reality, we actually deal with complex crystals, which are the union of many Bravais lattices. And the example at the end of my talk, there'll be, in fact, 18 Bravais lattices. And each one undergoes the same linear transformation during transformation, but there are displacements between the lattices. And in that case, the linear transformation is defined as the one associated with any one of those Bravais lattices. Okay, so most of the things I'm going to tell you come from a description of the free energy of the material, which is a function of the deformation gradient, 3x3 matrix, and temperature. The key point is it has energy wells. So at the transformation temperature, phi is minimized by U1, and it's also minimized by any rotation matrix times U1 by the condition of frame indifference, and that's represented by this circle. And same U2 and RU and rotation matrix times U2. And so in this case, the 6 variants of martensite are defined by these 6 matrices. There's the rotational invariance, which I've indicated by a circle. And there's the austenite phase, which is arranged to be at the identity. And so this circle is a representation of SO3. And we know those energy wells very well because we know by X-ray measurements those matrices to high accuracy. And there's a theory of symmetry which tells you the forms of those matrices and so forth and so on. It's not important for this talk. Okay. Now, so I'm approaching this fourth idea about hysteresis. This is what we see in many crystals which undergo reversible or semi-reversible phase transformations. It's widely observed. It happens when, as you'll see more about, it happens when the middle eigenvalue of that transformation stretch matrix is not equal to 1. And it says that the austenite phase, the cubic phase, this picture was taken in a single crystal, but it happens in a more complex way at the finest level in polycrystals as well. That's the cubic austenite phase, and this is in fact 2 of the variants of martensite alternating. So in moving this interface, the unit cubes of the austenite transformed in 2 different ways in the 2 bands. And you can analyze this from the perspective of energy minimization. So I'll do a hand calculation of energy minimization. So to be at one of those energy wells, so I'm going to minimize energy by minimizing the integrand, and you can be on one of those energy wells if you put the deformation gradient equal to U1 on one side of an interface and RU2 on the other side of the interface. As I said, U1 and U2 are accurately known. And that, to have a continuous deformation, a necessary and sufficient condition is that these 2 matrices differ by a rank 1 matrix. And that's, so these are given. R, A, and N are unknowns, and you work, there's an algebraic problem, you work it out, you get 2 solutions. And you compare with that picture, even at an atomic level, and it agrees very nicely with those 2 solutions. So you have very nice agreement with the normal to that interface, and the shape changes even at atomic level. And now you take the solution you just found, and you alternate the solution you just found on the laminate. I give myself a volume fraction F and a fineness 1 over K. As I let K get larger and larger, these layers get finer and finer, but keep the same volume fraction F. Over here, I put the deformation gradient on the austenite energy well, corresponding to this. And you can see immediately that no matter how I choose this rotation matrix, this is not compatible with either variant here, or with the previous solution. So I try the next best thing. I interpolate with a transition layer of width of 1 over K. So I simply interpolate two deformations. And I find that, in fact, you can drive the energy in that transition layer to 0 by making K larger and larger, as long as certain conditions are satisfied. So what has to happen is the normal to this interface is to be just right, and the volume fraction F has to be just right. And you work that out. So in fact, it turns out that if you give this previous solution, there are 4 normals which work, and they're corresponding to 2 values of F. Okay, so it's quite a rigid calculation. You compare that with experiment, actually it was a big deal because the normal to this is this is a so-called irrational plane, which means that it does not have small integers as its components in the cubic basis. So that's the result of that calculation. It nevertheless agrees very well in lots and lots of alloys with that calculation. So, but there's one thing about that calculation that does not agree with experiment. It says that you have to make these bands infinitely fine to drive the energy to 0. And of course, you can see from the picture, they have a certain fineness. And that's also understood in the sense that it's believed that there's a small, maybe the bigger picture would be better. Okay, there's a small interfacial energy on each of the boundaries of those bands, which is not taken into account by this calculation. As you make the bands finer and finer, of course, the total interfacial area, the total interfacial energy gets larger and larger. And so somehow this should compensate for the bulk energy, which can be made to go to 0 by allowing the twins to be finer and finer, allowing these bands to be finer and finer. So that's the explanation And there's further models which take that into account. But the bottom line in terms of this picture is that the theory without interfacial energy gets the answer quite, all the geometry quite nice. It misses the fineness, and the end result is there's energy in this picture. There's bulk energy in this transition layer, and there's interfacial energy on these bands, and what you see in the picture is a compromise between those two. Okay, and as I said, it's quite a rigid calculation. So it became a little clear a few years ago that hysteresis should be related to this energy stored in this interface that is due to the competition between bulk and interfacial energy. And you can imagine you have a crystal which is all austenite, and now you want to introduce a little bit of martensite. So there's a lower energy well for martensite, so you put some material in martensite, but as soon as you do, you're forced into having these interfaces, and therefore the additional energy, that's just because austenite is sitting next to martensite. Okay? So transformation is delayed because the additional bulk and interfacial energy that must be present merely because of the coexistence of the two phases has to be overcome by a further lowering of the well of the stable phase. But then you can also notice that, in fact, the middle eigenvalue of this matrix being 1 is necessary and sufficient that RU1 minus identity is A tensor N. That's the compatibility condition between one variant of martensite and the austenite phase. So if the middle eigenvalue of this matrix happened to be 1, you wouldn't need that transition layer. You wouldn't need those bands. You could have a perfect interface between the austenite and martensite, okay? And if you believe that the energy due to that interface or to that delocalized interface is what's causing the barrier for hysteresis, then what you should do is experimentally tune the lattice parameters of the material by changing composition so that lambda 2 equals 1. Okay, so we did that. And this is, in fact, this combinatorial data. And the result was absolutely astounding. The hysteresis was going down to near, this is the hysteresis, each dot is a different alloy, and this is the value 1. You can see it's, in fact, displaced a little bit from 1. That was understood because these measurements were done on films, and there was some stress in the films, and this was corrected for by the people who did those measurements. And but you can see there's some alloys which have one, around 1 degree hysteresis, which at slightly different compositions would have quite large hysteresis. There's a picture of one of those interfaces at high resolution, and in fact the normal to the interface was measured. This is the austenite phase down here. This is the martensite phase. And the normal agrees very well with the calculation, and the angle in Q is 3.8 degrees, and so forth and so on. So we see many of those interfaces in alloys which have been tuned to make lambda 2 equals 1. So those who are in lots of systems by now have been done, and it seems to be independent of material. So it's a way to make low hysteresis alloys, and we used it in a family of alloys called Heusler alloys, this is a perturbation of a Heusler alloy. Heusler alloys are famous because they have a great propensity toward ferromagnetism. So in fact, in this alloy, we changed composition and we got the middle eigenvalue this close to 1. We could do better, of course. But it's got about 6 degrees hysteresis, and it's got a transformation temperature, this is calorimetry, of around 135 degrees C. But what's interesting about this alloy is that the low temperature phase is non-magnetic, but the high temperature phase is magnetic. This should be magnetization here. This is the magnetization of the sample. And so when you go through the phase transformation, it becomes magnetic. But this is interesting because this becomes a really strong magnet. This is almost the strength of iron at a similar temperature. So this is a material that has low hysteresis. If It's non-magnetic. If you heat it up 6 degrees, it becomes a strong magnet. You cool it down, it's non-magnetic again. In that case, when we have also magnetism, again, there's again, everything I'll tell you is coming from this variational principle, which includes both deformation and magnetization. The energy wells are more complicated. There's actually many things to learn about this variational principle that we don't know, but we've done enough to help us guide us toward some of these new alloys and effects. So I'll show you what happens to that material. That's a sample of that material, nickel, cobalt, manganese, tin, and it's sitting on a little copper finger, and that's a permanent magnet. I'm just going to heat the copper finger, just so you see how it goes here. Okay, so it's kind of silly, but you can see that it's even though it's pretty far away from that permanent magnet, that's not particularly strong. It's enough to magnetize it. And then it follows the field lines over to the magnet. So if you imagine turning that on 90 degrees, it would be an example of energy conversion, because heat would be effectively converted into kinetic energy, and then as it got to the top, potential energy. But here's a more interesting demonstration that we did. We took a piece of that material, we put it on top of a permanent magnet, and we put a coil around it. And then you have to think in terms of Maxwell's equations, and you have this dipolar relation, B equals H plus 4 pi m, and you have the Maxwell equation curl E equals minus 1 over C dB dt. When you heat it, you go through the phase transformation. That gives you a big dm dt, which is, of course, partition between dB dt and dH dt. And how much goes to dH dt and how much goes to dB dt, that's micromagnetics. And we arranged by the shape and so forth that we get a big dB dt, and that gives us a curl E. That means there was a current in the coil. So we were able to convert heat to electricity. It's a pretty interesting method. We have an analysis of the thermodynamics. It works for a small temperature difference. So this is one of many ways to use phase transformations and electromagnetic properties for the direct conversion of heat to electricity without an electrical generator. Okay, I want to finish. I have 5 minutes. I want to finish with some more. So we realized, of course, that the compatibility conditions between phases affects not only the reversibility, not only the hysteresis, but as I'm not telling you about, it also affects the reversibility in a profound way. So we look for more stronger compatibility conditions between phases. And here's what we came up with is, again, we looked at that crystallographic theory of martensite that describes this as a minimizing sequence of some energy. And we realized there's a degeneracy there. So this was the standard situation. 4 normals and 2 volume fractions. We realized that if you satisfy certain stronger conditions, then you could have infinitely many solutions of this problem. You could continuously vary the normal, and you could continuously vary the volume fraction, and you would have low energy interfaces in the same sense as I described earlier. And it's, again, just conditions on the lattice parameters. It's just geometry. It's just conditions on the lattice parameters of the 2 phases. So these are the cofactor conditions. You have to satisfy lambda 2 equals 1. You have to satisfy a second condition here. And there's an inequality which is almost always satisfied. But it's quite interesting as you vary the volume fraction here from 0 to 1. Of course, there's the perfect interfaces on each end. That's from here. But as you vary the volume fraction, you have a continuous family of effectively 0 energy interfaces or low energy interfaces between those phases. There's many, many strains which are possible. And there's various cases, depending on which, you notice that this depends on the A and the N. That's the solution for the twin system. So how this looks depends on the twin system. This is the case for so-called compound twins. Turns out for type 2 twins, it turns out these conditions mean that the boundary between the bands is parallel to the interface. And there's another case, the third case, in fact, you can have interfaces in which there's no transition layer whatsoever. So in these cases, these are 0 energy microstructures. again, continuously varying. And you can also have curved interface with quite a few interesting things. So we worked very hard, and again, this is very simplistic. We had an alloy which was nearly satisfying these cofactor conditions. We changed its composition, and we checked whether we got closer to satisfying the conditions or not, and then we systematically marched toward these conditions. We were a bit lucky because we worked in this, our starting alloy was in the zinc, gold, copper system, and we were quite lucky because we satisfied them for two families of twin systems. That was an accident. Anyway, this is a typical tuned alloy, which is zinc 45, gold 30, copper 25, and in fact it has 0.2 C hysteresis. That's probably a record low hysteresis in a material, which this has like 8% transformation strain. It's a big first order phase transformation. So there's a sort of measure of the satisfaction. So I want to finish my talk by just contrasting some qualitative behavior. It's quite interesting behavior, this new alloy, and this is well. Let me show you what it looks like. What a typical transformation of heating and cooling a martensitic polycrystal looks like. It looks like that. Of course, I'm repeating the movie, but if you look carefully at the heating and the cooling cycles, you can see that there's quite a lot of reproducibility of the microstructure. In fact, that's been studied a lot by this group in Barcelona. In fact, they measure acoustic emission from, I guess it's related to the last talk in a way, that's emitted during transformation, and they find detailed correlation between the acoustic, even in detail, the correlation between the acoustic emission signatures is very similar. So this kind of detailed reproducibility of the microstructure in martensite polycrystals. So I'll finish my talk by showing you this zinc called the gold copper alloy, which has been tuned to satisfy these very strong conditions of compatibility. So I should warn you, this, you may not have seen many martensites in your life, but it is unlike any martensite that I have ever seen. So this is just heating and cooling the crystal. In fact, it's a polycrystal, looking at one grain in a polycrystal. And the most remarkable thing is every picture is completely different. There's microstructures here, like curved interfaces that we've never seen in phase transformations before. And it has about 1 degree hysteresis. So we hope that can open up the way to highly reversible phase transformations. So that's probably a good place to stop, Irene, because I'm done. Yeah.